So this is a short talk on simulating light in optoelectronic devices using Ogma Nano, and we're going to be focusing on specifically solar cells, sensors and biosensors. You can download the software that we're using in this talk from ogmanano.com/download, and these slides will also be available on that website. And if you've got questions or want to file bug reports, please do get in contact with me at roderickmckenzie@durham.ac.uk. So in this little talk we're going to cover what are optical simulations and why do you want to do them. They are the most easy and powerful way to analyse a device you want to understand, so an optoelectronic device such as a solar cell or a sensor or something like that. And they're very often the first thing you want to do before you want to look at any sort of electrical analysis or anything like that, because it really does give a lot of insight in a very, very quick way. I'm going to talk about why you want to perform these simulations, and we're going to talk about what you need to accurately do these simulations. So we're going to talk about the optical sort of input spectra, refractive indices, absorption coefficients, and then we're going to talk practically about how to do this with Ogma Nano, and sort of how to set up device structures and then run simulations, and that's it. So let's get going. So what are optical simulations? Well, there's an example of optical simulation there on the bottom left, and you can see we've got some light coming in from the right there in the green arrows. It hits a prism, it gets reflected here, and it sort of travels through the prism and refracts, which means bends. So it bends as it leaves and enters these objects. And you've got sort of transmission here, so you've got the transmission of light through the object, and you also got absorption, so where light's absorbed in the object. So you can see refraction where the light's sort of bent here, and you can see this refraction is the cause of this sort of effectively white light splitting up into this nice rainbow here. And you need to simulate all these sort of effects if you want to do optical simulation. So we'll just look at that in a bit more detail now. So I've labelled it here. So we've got reflection off the surface, so light's reflecting there. We've got refraction, where light's being bent as it leaves an object. We've got absorption as light sort of travels through an object. We've got transmission, where light absorption where light is absorbed as it goes through an object. We've got transmission that goes through the object. So those are sort of the key things you need to simulate when you want to model a device. And by the way, you can actually download this example simulation. It comes with Ogma Nano in the slide deck, in the demo simulations. So why perform optical simulations? Well, very often you want to look at, say, solar cells, design a solar cell, optimise its layer structure. You might want to design a biosensor, so you might be probing a biosensor with, say, a laser or something. You want to understand how the light distributes within the device. Or you might be designing an optical sensor, like a DVD sensor, a DVD sort of optical reader or something like that. It's very important to know, where your photons are in the device. So, for example, in a solar cell, if all your light was absorbed in the back contact, in the aluminium back contact, there'd be a very bad solar cell. If it was all absorbed in the active layer, it'd be a very good solar cell. So, you need to know where the photons are in your device. So here's a few examples of optical simulations. This is a solar cell. This is a PM6Y6 organic solar cell. So this is an optical simulation of where the light is going to be absorbed in the solar cell. So this is sort of all wavelengths together, and you can see there's quite a lot of absorption in sort of the back contact, but also a lot in the active layer there. And it's the same simulation as a function of position and wavelength, so you can see the sort of particular where the light's being absorbed in particular bands in the cell. Here's sort of a standalone optical simulation. So you've got light coming from the right, hitting a couple of lenses and going to a sensor. And you can imagine needing to do this type of simulation if you want to try and figure out sort of what lenses to pick in a lab experiment or something like this. I think this simulation is again available in Ogma Nano if you want to go and download it and play with it. And then designing filters. So I'm just going through a few typical examples here, but of course there's lots of other examples that you can probably think of. You've spent a couple of minutes thinking about it. So designing filters, or optical filters, that are based on these Bragg gratings, so sort of multiple high-low, high-low, high-low refractive index layers like this. And by tuning the gaps between the refractive indices in these various layers, you can make sort of band pass and band stop filters. So we've got transmitted light and reflected light, so it's much better to simulate this before you try and fabricate it, because you'll get a good idea of what the layer should be. And the same goes to make any device really. If you're doing sort of trying to optimise a solar cell or something like that, highly recommend firstly, before hitting the spin coater, highly recommend doing an optical simulation. So you got a good idea of what you're aiming for, what would be the optimum optical layer structure of that said device. So the wonderful thing about optical simulations is all you need is the optical input spectra, so if it's the sunlight or the laser light or whatever light. And the nice thing about optical spectra is they're readily available, so you don't really need to go and measure them. If you bought an LED to illuminate your device, almost certainly the spectra of that LED is going to be in the datasheet. The solar spectra is readily available. Spectra of laser are available. Most optical sources, the spectra is available. On the internet, so they're very easy to get. You don't need to measure it. What else do you need? You need the refractive index of your materials and the absorption of materials. So, refractive index of materials, again readily available, and if you don't have it, you can probably find something quite close to it. There's lots of good websites like refractiveindex.info, and there's absorption coefficients as well, how well the light's absorbed. They're readily available, and also readily available on papers and things like that. So you can go and measure this if you want yourself, but you don't need to. It's readily available. And your device structure, and if you've got all those four things, you're going to have almost 100% accurate simulation with very, very few variables, or no variables effectively, that you need to tune, and the results will be almost 100% correct, which is different to electrical simulations. There's a lot more nuanced, a lot more complicated, a lot harder to find out exactly what your electrical parameters are on your device. But refractive indices, absorption, very easy to find out. So very, very powerful, quick, simple thing to analyse optical properties of a device. So what you need for optical simulations, first let's look at these optical spectra. So this is the optical spectra of the sun, so the sort of intensity profile of it. So here you've got wavelength, here you've got intensity. This is grey line's perfect black body radiation, so that you expect from a perfect black body. The yellow is what we actually measure if you're in a spaceship at the edge of the Earth's atmosphere. So that's what actually hits the top of the atmosphere, the yellow bit, and the red bit is what you'd see at sea level. So where you're sat now on a good day. Probably not in the northeast of England where I'm sat right now. It'd probably be a lot lower than that, but that's sort of the ideal. The red is the ideal spectra you would see at sea level. And that's called the AM1.5G spectra, and you notice it's got these sort of notches taken out of it, and that's because of absorption of gases and things and water in the atmosphere. There's some gases in the atmosphere. So there it is. That's the AM1.5 spectra in detail. That's taken from the model from Ogma Nano. And as I was mentioning before, it's very, very easy to get hold of lots of different spectra of various light sources. So, for example, here's some LEDs, and these are some spectra I downloaded off the Thor Labs website. So when you buy an LED, almost certainly somebody's going to give you the spectra to it because they'll have measured it. Same with all these sort of white light LEDs and stuff like that. You can get the spectra very, very, very easily. So how do you access these spectra in Ogma Nano? You go to Database tab, Optical Database, and here's AM1.5G, and there's the spectra. Very often you want to import your own spectra because the exact laser or whatever it is won't be in the database. So just click Add Spectra, type in the name of the new spectra you want to call it. I generally try and avoid spaces in file names because it causes a bit of confusion sometimes. So I just put underscore there, specifically for cross-platform compatibility. So I just call it new spectra underscore, and you get this new spectra file. If you double click on that, you'll get an empty window up with no data in it because we've not loaded any data into it yet. What you can now do is if you go to, so I put a demo spectra here on the web. So I won't get that up now, but it's just a text file. If you download it yourself, you click on this link yourself, you'll be able to download. It's just a text file with 2 columns. So download that and save it to your home directory. Then from this previous window, just click the File button from File there, and you'll get this window pop up. And click Open Data File and open this data file that you've saved to your hard disk. And what you should get is a window looking like this. So this is the contents on the left hand side here. That's the contents of the downloaded file. So you've downloaded this file, you've saved your hard disk, you've opened it with this button, and this is what it looks like. And this is wavelength in nanometers on the left, and this is the irradiance in, and this is units of watts meter squared nanometers to the -1. Now, the idea of this importing tool is that Augment Nano only works in SI, so it only works in meters, seconds, watts, pure SI units. It doesn't deal with nanometers, it doesn't do micrometers, everything's SI in the model. So you convert whatever file format this is, so nanometers and not SI, and this is not SI, into SI units. So what you do is you select with this in this box here, you select wavelength nanometers because that's what this original column was in, and you select here intensity nanometers, watts, meters to -2 because that's what this original column here is in, and it will convert these columns into nanometers into SI units on the right hand side. So you can see 280 nanometers is 2.8 to the -7 meters, and we'll trust that it's done this conversion on the right hand side correctly. So here I am sort of explaining this a bit more detail. So you've got raw data on the left hand side, converted into SI on the right hand side, and just a zoom in of this box here just to make sure this is in nanometers and intensity. Now my advice would be to do, when you've imported this data, do a sanity check. Just look at the data on the right hand side and make sure it looks sensible. If you've got like zeros or negative numbers or nan numbers or infinite numbers or anything like that, you're doing something wrong. So just look at the data that you've generated on the right hand side and just make sure it looks sensible, because if it doesn't look sensible, your simulation is not going to work. If you got wavelength in sort of 10 to the 6, that's going to be wrong. So just take a step back and think, have I done it correctly before you continue? That's basically what I said there. So yeah, you can download this solar spectra. I suggest you have a go at that yourself, have a go at importing it yourself. Right, refractive index. So what is refractive index? Well, all things have this refractive index associated with them. So you might have done this experiment at school where you've got light going through a block of glass, and you could use Snell's law and sort of calculate how much the light bent. And you calculate things like critical angle and total internal reflection and refraction, things like that. And the refractive index of glass is about 3, that of air is about 1. So you can apply Snell's law and figure out how much this light's going to bend. So that's why refractive index is important. It sort of effectively controls the bendiness of light as it goes through an object. It controls other things too, but that's one important feature. And it's why, and this refractive index, this n, isn't constant. So here we go looking at glass. I think this is BK7 glass or something like that. The refractive index n isn't constant. It's not just 3. It changes as a function of wavelength. So actually, sorry, this is 1.5. So at 400 nanometers, n will be 1.53, and at 650 nanometers, n will be 1.51. And this change of refractive index as a function of wavelength is the reason that the light splits up as it goes through a prism. Is because light diffracts a different amount depending on what wavelength it is, and this is why you can see the light being split up as it goes through a prism. Refractive index also controls transmission and reflection through this equation here. So n1 minus n2 over n1 plus n2. I'm not going to derive this, but you just have to believe me that well, you can just do a thought experiment. So if the refractive index of this layer is 1, and the refractive index layer of this layer is also 1, so 1 minus 1 is 0, so there'll be no reflection. And you look at the other extremes and sort of play with these numbers and try and convince yourself that this formula does actually control how much light is reflected and transmitted. So I'm not trying to give you a course on electromagnetics here, I'm just trying to sort of point out some things where refractive index is important. So it's important to control how much light is transmitted and reflected at various layers. So now let's look at the absorption spectra. So that's n, which is important, and let's look at the absorption spectra. So what is absorption? Well, we've got a good example of absorption here on the right hand side. You've got a laser shining into some sort of a liquid, and you can see that it hits this liquid, and then the intensity of the beam decays as it goes into the liquid. And this is because this green laser light is being absorbed in the liquid. You see right down here there's no light because it's being absorbed. And if you plot this out mathematically, you can use this equation. So I0 is the intensity of the light here, exponential, that's exponential. X is the depth, so this depth down here, so you can see 1 centimetre, 2 centimetre, 3 centimetre, and A alpha is the decay coefficient, so effectively, or the absorption coefficient, and it's how rapidly this light is absorbed. So if alpha was really, really high, the light will be absorbed in this top layer. If it was a bit lower than what it is here, it reached the bottom of the glass. So this is absorption. Now, just like refractive index, absorption changes as a function of wavelength. So depending where you are, is depending what wavelength is absorbed most. It's why if you sit in a car, you're protected from UV radiation, because the glass takes out a lot of the UV radiation and lets the visible light through. So glass is very absorbing, around about sort of 300 nanometers. So yes. Now, this alpha, this absorption coefficient, has the units of meters to the -1. It has meters to the -1, so this is very important. And generally speaking, for materials like solar cells and sort of organic polymers and stuff like that, your absorption spectra should have a peak around 1 to the 7, 1 to the 6, 1 to the 7 meters to the -1. If it doesn't, think carefully if it's correct and think if the conversion has gone correctly. This isn't true for everything. For example, ITO might be much lower, but organic stuff generally will peak around 1 to 7, 1 to 6 meters to -1. Now, very often, absorption coefficient, so we've been talking up till now about this, I'll just go back one, about this alpha coefficient here, which is in meters to -1, and that's a plot of it there. This is the quantity that Ogman Nano uses in the model to deal with or to simulate absorption. But quite often you'll find absorption data given in different units, so it might be given in this attenuation coefficient K. Now, I don't want to get into this too much, but all I want to say is that, and you can read about this, and it's to do with the fact that refractive index is actually a real plus imaginary part. But all I want to say is that alpha, so the absorption coefficient in meters to -1, what we've been using so far, is linked to attenuation coefficient K by 4 pi over lambda. Now, so in the literature you'll find alpha and K, and this is how to convert between them. And a trick experimentalists quite like to do is they like to normalise their data to 1, and if they do that, then you can't import it into the model because they've lost the magnitude term. So that's quite annoying when they do that. But assuming they've not done this, and you have a file with K in, you can actually automatically convert it to alpha by just setting the attenuation coefficient here, and that'll convert it to alpha. So let's have a look at the materials database now, where we import all this information. So again, the database tab under materials, and we can just sort of have a look at it. So we go sort of polymers, then click on say PTB7, and this is what it looks like. This is sort of the absorption coefficient, and there's also a refractive index there. And you sort of click on the various tabs, you can see the absorption of the material, the refractive index, and notice this import from file button where we can import the data just like before with the solar spectra. Also other tabs here that are quite useful, sort of the colour of the material and thermal properties and a few electrical properties that is sort of used to various things. So moving on. So just we're going to run over importing NK data into the model, because I think quite a lot of people want to do this. So if you want to do this, click Add Material, click, and it'll ask you effectively what you want to call your material, just like before. You open your new material there, and you'll have basically a flat line with no data. So just what you need to do now is you need to download. So I'm just giving you an example here. I mean, you can get this data from lots of other places, as I said, places like refractiveindex.info, it's refractive-index.info, I think. You can get refractive index and NK data from there and whatever. So if you download this file, the zip file, you'll see two files in the zip folder. You'll see N and K. This here is N, so we've got wavelength in nanometers against refractive index. And PTB7 PC70BM is just an organic material used for solar cells. And then here in this K file, we've got wavelength in nanometers again against complex refractive index K, or this attenuation coefficient. So what we're going to do is have a go importing this K file, because I think this is the most complicated one to do. It's simple, but it's the most complicated one. So again, you go import data, just as before, and then you select the K file, so it's k.csv, you go and find that, and it will import it into this importing wizard, just like we did before. So just like before, this is the refractive index, this is the wavelength in nanometers, this is the complex refractive index, K, this is the original data, this is it converted into SI units, and you can see this is, again, so 300, about 300 nanometers is 3 times 10 to the minus 7 meters, and here we've got numbers round about 7 to the 6, some numbers is peaking about there, and to get it to do that transform, I chose wavelength in nanometers and then attenuation coefficient. You then click import data there, that's the key thing, to import the data, and so you click import data and it will have imported it. I don't think I show a picture of it being imported, but you have to believe me, it imported it into the model. Right, so just trying to remember what comes next. Yes, so we're going to look at solar cells in this next example, and solar cells are sort of multi-layer structures that are quite an interesting thing to simulate. So we're just going to run through some of what we learned and apply it to solar cells now. So there's lots of solar cell examples in Augment Nano. If you click new simulation and say select a PMY6 solar cell and save it somewhere in your home directory, you should get this pop up. So you've got a little picture of a solar cell and you see the light coming from the top, and you can and if you click on the layer editor there, you get effectively all the layers that make up this solar cell. So we've got ITO, ZNO, an active layer, moly oxide, and some metal on the bottom. And these are layer thicknesses. So you can sort of edit the layer thicknesses, or you can add in new layers. And if you use these little buttons here, you can choose a different material. So you know, if you add in a new layer with this button here, change the material. This name here doesn't actually mean anything. It's just an English name, so you could call this like Fred or Bob or something, it wouldn't matter. This is just a label for it. The things that really count are the thickness and the optical material. The other thing I'm just going to quickly run over is this layer type. You've got the contacts, which are self-explanatory, and then if you choose active layer, that means you're going to do electrical simulation over that layer. So if you want to just add another layer, for example, to check what how it changes the optical coefficients, don't select it as active, just select it as other. Only if you actually really want to do on electrical simulation on that layer, set it as active. And I don't want to get into this now too much, but people, when initially doing simulations of devices, people think, well, there's electrons and holes flowing through all layers in the device, therefore they all need to be electrically active. That's not true. Only the real semiconductor layers are usually set as electrically active. I'll talk about that in another video, but typically don't set everything electrically active. Suggest in the most basic devices you just have one layer as active. Okay, here we go. I've actually detailed it here. So I've got layer name, explain that, thickness of the layer, optical material, this points to the NK data file and database, and other columns, we'll discuss it elsewhere, as I said. So what I suggest you do now is increase the active layer thickness of this 300 nanometer layer, and you can sort of maybe change what material it's made of. Little fire alarm there. I don't know if you heard that on the video. So yeah, and you can change what material it's made of there. So now we're going to talk about running optical simulations. So to run the optical simulation, you go to the optical simulation tab and you click Run Optical Simulation. And this particular device is set up with you can see I think there's a laser there at sort of 500 nanometers. That's green. So this is just the absorption of that particular, very narrowband laser. So if you click Run Simulation, you'll get this up, and you can check out other tabs in this window where you've got sort of where the light's absorbed, and so you sort of look at it, where the generation is, where the photons are, and you sort of analyze it in detail to figure out where is light being absorbed as a function of wavelength or position or what have you. Final thing, we'll talk about light sources. So is that slide unfinished? I believe the slide is unfinished. So this slide is slightly unfinished, so I'm just going to talk you through it. So if you go to the optical tab, you'll see this little lighthouse thing called light sources. So if you click on that, the light source tab looks like a little lighthouse. You'll get this window up. And currently, the light source is set to Thorlab's 515 nanometer laser. That's just the laser that I was using for that particular experiment. So what you can do is if you click on that little download tab, that little tab there, you can select any of the light sources that we have in our experiments in our database. So here I've just selected AM1.5G, and if you click this little rebuild button, it will display the new spectra. So this is the solar spectra. I don't know if I go into other options in here. I don't go into other options in this little talk, but you can apply optical filters. So for example, you can apply bandpass filters and things like that. There's other various configuration options. You can also sort of push in an external interface, so you can have reflection off some sort of glass before the light hits the solar cell if you so wish. But in principle, this editor that's accessed through this light source tab is used to manipulate and choose the spectra that you want to be used. So if you then go back to the optical simulation and click run the simulation again, what you'll get is the full AM1.5 spectra now applied to the cell, and you'll be able to sort of see the difference between what happens in the absorption profile there to what happens when you just apply that very narrow laser to it. So that's it really. There's also options here in the config window to apply light from the bottom or top of the device and things like that. Moving on. Output. Let's look at outputs a bit. Oh, the danger of just flipping back a bit too much. We're going to flip back one more slide. There's different types of optical model you can apply to the device. So this is a full transfer matrix simulation. You can also do an exponential profile. You can do a flat profile. You can get the profile from a file, or you can just set constant values for generation rate. Often you want to use, this is a full transfer matrix model, which is very accurate, very quick, very accurate. But often you want to try and understand the results using a more simple model, maybe because you're trying to understand a particular electrical effect or something like that. You want to sort of remove more complex effects, and you can do this by choosing an exponential profile or a flat profile. Outputs. So let's look at the outputs. So this file here in the outputs, in the output tab, called optical snapshots. And if you run a full simulation and scan, you get this window up here, and you scan this bar along, you can see where light is absorbed in your device as a function of wavelengths. You can sort of select if you want generation rate or photon density or whatever, and you sort of view this as a sort of a slice through each wavelength, which is quite nice. And if you click the play button, it'll do that for you automatically. Siminfo.dat, this gives you stuff like the maximum potential photocurrent. So if all the photons were converted into electrons, that gives you sort of the maximum current you get out of your solar cell or sensor. And this file, lightstats.json, will tell you how much light, what fraction of light is absorbed in each layer. You can't actually, I don't know if it appears there. Where is it? Can I see it? It's probably in here. I just can't see it. Oh, yeah, lightstats.json there. I'm not sure that will open in Augmenano. If you double click on it, you might need to open that with Notepad or something externally. But it looks like this, and it will tell you where light is absorbed in each layer. So finally, also this file transmitted and reflected, where you can look at how much light is transmitted and reflected from the device. So summary. I don't know if there was a summary. Yeah, in this talk we basically covered the fundamentals of, let's go through it. I guess importing data, what refractive index is, what absorption is, how to convert between alpha and K, how to run optical simulations, and how to examine the output in Augmenano. So I hope you enjoyed that little talk. I hope it was useful, and drop me a mail, or if you've got questions or if you find any bugs. Thank you very much.